I'm Joe Haley. I'm from St. Cloud State University in St. Cloud, Minnesota. Happy to be here at the Wolfram Tech Conference 2016. My presentation is about using directional bit sequences to display the property and liability underwriting cycle as an algorithmic process. Thank you. I'm talking about the property and liability underwriting cycle. Property and liability underwriting cycle is simply a profit cycle for the underwriting activities in the property and liability industry. You can see I got the data there from 1930 to 2000. It's kind of old, but I had some continuity problems I didn't want to take time to mess with, so I stuck with the 1930 to 2000. Underwriting cycle or profit cycle for property and liability just deals with their profits on their underwriting activities. They sell policies, they collect premiums, and they pay losses. And that's known as their underwriting activities. The graph shows the underwriting margin. So a margin of 5 means for every dollar in premium, you paid 95 cents in losses and expenses on that graph. So you made a nickel for every dollar of premium. The aggregate, you can see it in the graph here. The aggregate profits are characterized by irregular fluctuations. I want to emphasize irregular because there are some people in the insurance area that, in the academia, that trying to get rid of the word cycle because it's not regular. You know, it's not like 3 years down, 3 years up, or whatever. I don't get caught up in those conversations. Everybody I know in the industry calls it a cycle. And the cycle fluctuates, hard market and soft market. Hard market gets its name because it's hard or difficult to get coverage. Rising prices, restrictive underwriting. Restrictive underwriting just means insurance companies are more careful about who they sell a policy to, who they let into their risk pool. And then the soft market's the other way around. Falling prices, liberal underwriting. They'll let anybody into their risk pool. They'll sell their policies to anyone. Or not to anyone, but they're more easily convinced to sell one. Theoretically, profits should behave more randomly. I mean, this is why the underwriting cycle becomes of interest, because theoretically the profits should behave more randomly because the losses are very random. Losses are very random. But you can see that there is a cycle there. So, what I did is I created a simulation, and then I needed to figure out if my simulation was sort of accurate. You know, I mean, is it representative of the real, of what really happens? And so some important features. Only pure premium is modeled. Pure premium is just the dollars that the insurance company collects to pay losses. A premium is made up of multiple parts. It's the pure premium, the expected losses, and then it's got expense loads and risk loads on it. Okay, I'm ignoring the expense loads and the risk loads. So for me, equilibrium would be profit margin of 0. You collect just enough loss dollars to pay for losses. You collect just enough premium to pay for losses. There would be a risk load on top of that that turns into profit, but I'm not doing that. My simulation is agent-based. Individual insurers following a pricing rule separately. As you'll see, I've got 75 insurance companies in my simulation. Each of them are acting on their own. They're all following the same pricing rule, but they all have their own circumstances, losses and target capital structure. Capital structure is just the mix of equity and debt, and each company has a target capital structure. An example would be a 40% equity, 60% debt. The only debt that my insurance companies have are losses. So they sell a policy, they immediately create a contingent liability of having to pay a loss. And so in the 40-60 structure, you start off, you got $2 million in equity, so that means you're going to sell $3 million in policies. because the goal is to break even, collect just enough money to pay losses. So you'll sell $3 million in premium and have a matching $3 million in expected losses. So you've got $2 million in equity, $3 million debt. The insurance is mandatory, and the industry faces a downward sloping demand curve. I just kind of got, rather than stick the formula up there for the demand curve, I just stuck these two graphs. The one on the left shows a wide range of prices, 50 to 35, 375, and so the demand curve is convex, and the other panel B has a narrow range of prices, 50 to 75, so the curve appears quite linear. One thing to keep in mind with the demand curve, every insurance company gets at least a customer, at least a small batch of customers. So even if some insurance company charges a really high price, they'll still get a tiny part of the market, which isn't that weird. I mean, companies will start charging higher prices and their customers are loyal. So what happens with the simulation? I forgot. I need to go talk about the pricing rule. This is why I call it an algorithmic process. It's probably about the most simplest version of an algorithmic process you might have seen. It's just they charge a premium based on three things: expected losses, last year's surplus, which is the insurance word for equity, and last year's size of risk pool, which is the number of customers. The expected losses is a constant. I say approximately 3,123 because that constant actually changes from simulation to simulation. But when I run a simulation, expected losses is determined in the beginning and then it's constant throughout. Last year's surplus is just the equity, last year's equity. And then size of risk pools, number of customers. You can see the pricing rule. Don't need to go through that a whole lot, but you can see it's simple. It's pretty simple. And the R there, that's the target capital structure, surplus over assets. How many of your assets are you holding as equity? What proportion? Premiums are collected at the beginning of the year, losses at the end. So there's actually a 2-year lag because you have the surplus from T-1 feeds into the price right now, and then losses don't get paid until the end of the year. So it's actually a 2-year lag. 2-year lag by itself kind of explains why you get a cycle instead of just randomness with the losses. And losses are simulated using skew normal. Actually, it's mixed with skew normal mixed with binomial. So you wind up with a big list of mostly zeros and then like 5% losses. And that's how those insurance companies on their commercials claim to have a 95% customer approval, because 95% of the customers don't have any claims, don't have any losses. All you got to do is not make them mad and they'll approve what you're doing. Okay, results. 75, and I just call this simulation X. We'll show some others, but 75 companies for 200 years. You can see the graph on the left. That is the aggregate underwriting cycle, the simulated aggregate underwriting cycle. The one we saw before was the real one, and you can see that it's a pretty regular kind of cycle. If you count trough to trough or peak to peak, you usually get 6, but not always. Every company starts off in equilibrium. What I do is I give every company 100,000 customers, and then they know their expected loss, and then I just give them a surplus that'll match their equilibrium, that'll match their target. You can see that the average loss per insured is on the other one, and that's very random and it's not cyclical at all. So why am I doing all this? Well, I generated the simulated cycle, and I wanted to compare it to the actual. And I was thinking, well, if it matches up with the actual, then I can say my rule-based price, my price rule is sort of accurate. Excuse me. But if I do a usual comparison of this, there's 200 years and the other one is 71 years. If I do a usual comparison, there's nothing compared. It doesn't match up at all. There's no correlation, there's no nothing, no lag correlations, no nothing. So then I thought, well, maybe I'll compare them. And this was the promo for this conference said, if you think you did something clever, okay, so this is my clever part. I compared these time series with what I call directional bit sequences. I got the idea from an article by a gentleman named Hector Zenel, who I believe has worked or does work with Wolfram. Hector Zenel and a guy named Delahaye. They do something very different from what I'm doing, but they did create this directional bit string, which is what gave me the idea. So I do a four, or at least what's reported here is a 4-tuple directional bit sequence of the actual underwriting margin and the simulated underwriting margin. 1 is up, 2 is down, 1 is up, 0 is down. And so on my graph here, so you got we got 4 bits in the string, and so there's 16 possibilities. Point 1 is 1, 1, 1, 1, which is up, and then point 16 is down, 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 down. If you look at the graph, you can see that up never happened at all with the actual data. The solid line represents the actual data. The hash line is the simulated data. The graph also is a discrete graph, but I connected the lines to make it look prettier. And anyway, you can see they match up pretty well. The 4-tuple directional bit string from the actual data and the simulated data match up quite well. I did 2-tuple, 3, 4, 5, and 6, and they all pretty much the same. I just liked the 4. And you can see correlation, 0.9. And so now I'm saying they have similar structures here. The actual data and the simulated data have a similar structure with regards to the direction of their movement, and which is important because I never mentioned when you looked at the simulated bit string, the simulated underwriting margin, it did tend to equilibrium. It was bouncing around 0, which was equilibrium. The real industry, I've done some other research, the real industry, people agree, pursues equilibrium. So I'm saying that these 2 time series pursue equilibrium in the direction of their movement. What about some other simulations? Well, quick look at 4 others. I've done dozens, and they all look the same. Correlation's a little bit different. That one's got a correlation of 0.86. It's real unusual for me to get anything under 0.5. Under 0.85. It's real unusual to get anything under 0.85. So the simulation is generating this time series that matches the real world. So I'm saying that the direction of the changes are the same. Okay, well, what about the way the time series are distributed around equilibrium? So what I want to do is look at the shape of the simulated time series. You can see the simulation X, and you look at that by itself, and that doesn't matter too much. You can see what it looks like. But how about those other 4? Well, those other 4 simulations have way different shapes, right? And so what I'm concluding here, and you can see on the next slide, is the behavior around equilibrium is very different. There's no consistency to it, which, of course, as trained as an economist, I would tell my economist friends this all the time, and they wouldn't always believe me. But pursuing equilibrium in the 1970s, no matter what you're talking about, is different than pursuing equilibrium in the 1980s, right? And 1990s and the 1930s. The market is always going to equilibrium, but if it goes fast or slow, there's so many factors that go into it. And so I'm saying, well, now my simulated data matches the actual, but but I'm going to separate the notion of a probability distribution that governs the data. So some initial conclusions. You have this common structure. Common structure shows the underwriting cycle following a rule-based process. We're continuously seeking equilibrium. And then number 4 there, the usual notion of a continuous probability distribution being the basis of a data generating process on the time series is relaxed. Okay, that's a nice way of saying, okay, let's forget about it. Right? And the last one, the actual underwriting cycle we observe, because we ran the simulation over and over and we observed different things, different distributions about equilibrium. The actual underwriting cycle we observe is just one of many, many possibilities. I joke with my students, YOLO, you only live once. That path that you see, that's just what you just happen to see. There's like 1,000 or 1,000,000 or infinite possibilities that could happen. So I like this conclusion, and I thought, well, can I move forward? Can I look at other parts of the simulation and see if it means anything, or if I just get something goofy? Okay, first I looked at companies. The individual companies, how do they behave with regards to the industry? In economics for a while went through this representative agent stuff that I didn't like. But anyway, you can see here there's 4 companies that I just picked. One on the upper left is pretty correlated with the industry. The one on the bottom on the left is negatively correlated with the industry, and then the one 0 and the other one's in between. And so since we have an agent-based model, and what we have is that we have microeconomic decisions that can't be deduced from macroeconomic. Right? We can watch the results for the industry, but the individual companies are all doing their own thing. Okay, they're all following that pricing rule, but they all have their own circumstances. They're their own random losses, their own target capital structures. And so I asked the question, and then my answer is, yeah, sort of. But I asked the question, is this evidence of emergence? And I would say, yeah, sort of. You got the individual companies doing their own thing, and then you got this aggregate behavior that makes it look like the companies are all working together. Kind of the classic bird flocking idea. An importance there is the downward sloping demand curve puts discipline on the behavior. Okay, now something else to look at, volatility. This is an aggregate margin. This is not simulation X. I picked this simulation because right around t equals 125, the market becomes more volatile. I mean, you can see it. But also, if you look closer, or if I do more calculations, the correlation across the companies goes up in periods of volatility. Right? Well, that has some intuitive sense to it. In periods of volatility, companies start behaving together. In the property and liability industry, they'll talk about the race to the bottom. Some companies will start cutting prices, others will start following it, and before long they're way low. They're way lower than they need to be, and then they all raise their prices together. And then they get accused of collusion. That happened in the 80s. And it happened in the 40s too, I believe. So anyway, periods of volatility, the companies start behaving together, right? Which has some intuitive sense to it. Okay, now, I also decided to look, again, I'm looking at the simulation, trying to see if there's other pieces that make sense. I like the directional bit sequences and the simulation pursuing equilibrium like the aggregate. So what I did was I ran some additional simulations, size 15, 35, 55, and 75 companies. Thank you. You can see, well, first off, you can see that when the standard deviation is greater, in general, when the standard deviation is greater, the average correlation across companies. Now, what I'm looking at here is the underwriting margin. the profitability. So when the standard deviation is greater, the company's profits are more correlated. The companies are moving together as profits directly related to price. But also, there's the tendency for an industry with smaller number of companies to be more volatile and more correlated. Then, because up here they got a 15, 15, 15, 15, 15, 15, 35. I think this is a 35, 35, 35. And then down here we got a lot of 75s and 55s. It's not perfect. You can see a 75 here and a 55. But anyway, the industries with the smaller number of companies tend to be more correlated and more volatile. Well, that has some intuitive sense with it as well. A company with an industry with a fewer number of companies is less competitive. You can, if you have a couple of companies start moving one way, then everybody sort of follows them in terms of price. So here's a CDF of the simulation. 75. It's going to change as soon as it runs through, but it takes a while. 75 companies. 200 years, you can see its volatility. You can see the bit strings line up. I also, on here, that orange line, that's just random data to show that the bit strings that are matching are separate, are distinct from just random data. And the correlation of the bit strings is 0.88. Correlation across companies is 0.32. Whoop, just changed on me. Correlation across companies was 0.32, which was a little bit high for 75. Let's see what we get here. This was another 75 companies. Directional bit strings, again, they match up almost all the time. Correlation of the bit strings, 0.88. Correlation across companies, 0.26. That's still that's probably just slightly higher than typical. These two numbers, this one here, the weighted average of underwriting margin, should be 0, which it is. This needs to be 0 too, just kind of as checks as to things going okay. Average underwriting margin should be 0, I mean the industry's pursuing equilibrium all the time, and there shouldn't be any correlation of losses across the industry. Let's do a 15 company. That shouldn't take too long. Unless you're really tired, then it seems like it's long. Here we go. Now this one's very volatile. This one looks very volatile. It's all the way up to 5%. The directional bit sequences, again, match up as almost always. Correlation of the bit strings, 0.88. Seems to be hitting 0.88 all the time. But here, with the 15 companies, look at the correlation across companies, 0.78. Right? That market with just a few companies, 15 companies, small number of companies, became very volatile. Everybody's behaving together, and we have very correlated activity. So, I know you want to go to the reception, so I won't do that CDF again. That's nice and slow. So anyway, conclusions again. I say that the underwriting cycle can be modeled as an algorithmic process, which means that we don't have this data generating function for the time series, right? Equilibrium has a gravity-like pull on the economic activity, which we always hope for with economics. But the movement towards equilibrium isn't uniform or symmetrical through time. Some deviations are adjusted to very quickly, some are adjusted very slowly. When it comes to economics, there's always 1,000 factors you can't even figure out that influence these things. And so I'm really just trying to say that we'll analyze the changes separate from the magnitude of the changes. There's no data generating process. The companies follow this rule about pricing, and so the next step, I haven't really done a whole lot with it. The next step then would be to study the just the changes, the magnitude of the changes around equilibrium. The speed at which they adjust, but how that's kind of random. I would use the phrase stochastic volatility, but that'd be outside my skills. Each company following the price rule, industries operating along the demand curve, a type of emergence occurs. Company activity is more correlated during periods of volatility. We all kind of learned that in the financial crisis of 2008. Everybody started doing the same thing. And an industry with fewer companies prone to more volatility, less competitive. That's a kind of a standard economic conclusion as well.